Hello, I am Signar Baez, Principal Architect for MongoDB, and I would like to walk you through our proof of concept on how we can help customers migrate off of their mainframes using Google Cloud and MongoDB Atlas. Our story begins with the future state. Our customers want to provide their end customers with the best systems of experience, gaming, commerce, collaboration, and so on. The future state is one where our customers can seamlessly access data from the mainframe for new applications in the cloud and modernize legacy mainframe applications. The best way to achieve this is by architecting and deploying an operational data layer. To build an operational data layer, or ODL, customers will want to use the best data platform, which is MongoDB Atlas, running on one of the top clouds, which is Google Cloud, and enrich their data using one of the top modern data warehouses, which is BigQuery, that itself is powered by BigQuery ML. But in order to achieve this, these customers must first unlock decades of data that is locked in their mainframe, and also modernize decades of application code that is locked in COBOL programs. Google's G4 transform can unlock that application code by generating Java out of COBOL programs. In addition, our customers can also build new digital applications on a modern stack. And both of these types of applications can obtain their data from the operational data layer built on MongoDB Atlas. For our POC, we wrote a set of COBOL programs that implement all of the data operations for a sales order, and it uses IBM DB2 as its legacy database. We then transformed the COBOL programs using Google's G4 and obtained Java application code that still uses IBM DB2. We then further refactored this for cloud and microservice in a modern stack using Java, the Spring Framework, which is Spring Boot and Spring Data, and then hosted the application on Google App Engine and of course on MongoDB Atlas. In terms of the data, we use Informatica to ETL and transform the relational data into MongoDB rich data structures stored in JSON. Let's do a quick overview of Google's G4. As we all know, all COBOL programs have various divisions: identification, environment, data, and procedure. G4 can parse your COBOL code and understand which programs operate against which tables or data entities and what operations they do, essentially building a CRUD matrix. It also understands and builds the call flow between programs in an effort to build a hypermodel of all participating programs and CRUD operations against data tables or entities. Here is an example of actual input and output of G4. On the left-hand side, we have an example of a COBOL copybook, which is essentially the definition of your data tables or files, and also example of COBOL code executing statements against the data. On the right side, we have the resulting Java entity class, or POJO, as well as Java code that manipulates data. And now, Robert Bereps from Google will demonstrate an actual transformation.
So we can select the programs that we would like to convert. So just convert them all. So now the converter is running and it will go through the different phases. The second phase is the parsing, and I can demonstrate you that. So at the right-hand side, you will see the COBOL source, and at the left-hand side, the parse tree that is generated from it. So for every COBOL program, we will create or generate the parse tree that shows the entire context. In this way, every program gets decomposed, and then the converter takes up all those parse trees and starts transforming them. The result of that process will be stored in the converted sources subdirectory. So this is now the code that is generated. Every COBOL program will be split up into 3 artifacts, 1 interface, 1 implementation class, and often another implementation class containing the working storage section or the records from the working storage section. And if there is no record in the working storage section, no class will be generated for that. So if you open the program and the related original program, so what's the name, complete or the delete. It seems that often the names that are in the program are different than the source file. So the original program at the left-hand side, the converted one at the right-hand side. Connect statement is not converted. Normally in a COBOL program you don't see a connect statement, so that's done via the environment. So that's why it's not converted. And then it's quite straightforward. Move statements are converted to an mset. Call display statements are converted using a builder pattern because you can have different options. Embedded SQL is converted to Fluent SQL API. But that's something that can be changed. So if necessary, we can generate repository classes by finding the main table of a query, generating a repository class for every table, and moving the SQL code to that repository class. The placeholders will, in that case, become parameters, and the method that we generate in the repository class will return, for example, a list of entities.
Now let's walk through the refactoring for modern cloud and microservices and MongoDB. In the tabular or relational data model, your related data is actually split across multiple records and tables. Every time you read, you have to join and read from different places. Every time you write, you place a lock on the database and write in multiple places so that everything is saved as a single unit of work, normally called a transaction. Both of these actions affect performance. Additionally, the schema is rigid. It has to be defined up front before we can write application code. In other words, the schema drives what the application can do and not the other way around. With MongoDB and the document data model, your related data is now contained in a single rich document. It is stored efficiently in binary form, we call BSON. Any field in your documents can be queried or a combination of, and you can also build indexes so that your queries are efficient. In other words, your data that works together now lives together. And in mainframe offloading, there are other types of databases: VSAM, ISAM, IMS, IDMS, etc. All of these should be taken into account as we go through data modernization. The first part of reaching our final state is the data modernization. We converted your traditional sales order header and sales order lines, 2 tables, into a single MongoDB collection. And now all data about a sales order is contained in a single rich document. Here is the actual transformation using Informatica. First, let's create a JSON schema that defines our sales order using Informatica. After we bring the order header and order line items from DB2, we can use the hierarchy builder to define the mappings of the transformation. First, we use the hierarchical schema that we defined earlier. Here it is. And then we choose the mapping of the fields and associate the source tables, header and line, into the hierarchy builder. We can then associate the primary key of the header table against the foreign key of the line table. And this is what Informatica will use to determine which line records will be embedded as elements in the embedded array, essentially for every order. After that, we just continue building the hierarchy of our document and mapping fields from either the header table or the line table. And it's obviously Informatica is an amazing tool, and all of this is done visually by simply dragging and dropping all your fields and continuing with the mapping. We can then add a target, and the output of the hierarchy builder will be the input towards the target. And the target obviously becomes MongoDB Atlas. We've already defined that connection to our cluster up front. We simply choose that cluster, wait for the connection to appear, and then choose the database and your collection, and then essentially map the output of the hierarchy builder towards the destination. And in our case, we're simply going to take the complete output and send that over into the document. So we essentially just have the ID and now the document transformation. And that's it. It is done. Our mapping is done. And we can now go and run the actual ETL. Okay, let's go ahead and run. We choose our Informatica runtime environment. We've already selected the mapping. And simply execute. And now we can go to our cluster in MongoDB Atlas. And here is our data. It is transformed. All my sales order headers and my sales order line items are now embedded. Done. And in terms of app modernization, mainframe modules can be converted into microservices that can be hosted on Kubernetes engine, run as a cloud function, or hosted also on Compute Engine. And they can either share or have a dedicated MongoDB cluster, and they can be orchestrated using an API platform such as Apigee. We then refactored the transformed code that was procedural and resembled the original COBOL programs into a modern microservice that is cloud native. Spring Boot and Swagger provide the API surface, essentially handling all the HTTP verbs and communication. Spring Data and MongoDB Atlas provide the data layer. Everything is written in Java and hosted on Google App Engine. Let's walk through the app modernization. Let's start with one of the transformed Java programs. This is the equivalent of the sales order line update. It performs essentially or adds line items, executes a transaction, updates the sales order total, and another transaction. Let's see the equivalent of that in the microservice. So here is my REST controller using Spring Boot. All my routes, all my API endpoints are under the /API. That's very traditional for REST API controllers. For example, if I want to get a sales order by its ID, then we would execute an HTTP GET /API/sales order /the ID. Let's look at the how we can add line items. Here is my post line items method, and if I want to add a line item to an existing sales order, I will do a post into sales orders, the ID and line items. So I'm essentially posting or adding new line items into an existing sales order. The controller then passes down control to the service class. The service class then relies on the repository to obtain all data it needs, in this case finding the sales order, performing some basic business logic in code, adding the line items, calculating the total sales order price, and performing the update and returning the updated sales order. Notice the code is very clean and very simple. And done. Now let's see the microservice running for real. Here is my Google Cloud Console. I'm in the App Engine panel. Here is my App Engine. There are 2 instances deployed, and as you can see, it was done by me. Here's my dashboard. There is a little bit of traffic as I was executing the API endpoints. Let's go over into Swagger. So this is the endpoint, and Swagger actually generates this nice UI for us so we can test out our API. We can browse our model. So here's our sales order with line items and with addresses. Great. Let's drill down into the sales order controller. Here are all of my routes. Let's say we do a get of sales order 10,000. Let's try that one. 1, 2, 3. And there's my sales order. Okay. I'm going to try and post these same line items as new line items. So let's go into a different route. Let's use the post of the line items. Okay. So try that out on order 10,000. And let's paste the same line items. And we should get an error not allowing us to post existing line items. And indeed, we got a 409, and the response says we cannot add a line item that already exists. Let's go and change that to line item 3. Or actually, let's also change the actual item. So this might be tools version 2. And this will be line item 4 with maybe home and garden. Okay. Oops. And let's execute that. And indeed, we now receive a 200 and we have an updated sales order. And now let's go and get that sales order again here. Execute. And correct. My sales order has been updated with 2 new line items. There it is. So my microservice for sales orders is fully running and using MongoDB Atlas. Let's actually go into Atlas. And here it is. This is an Atlas cluster running the latest MongoDB, which is 4.2.8. It is deployed in GCP on US Central 1, which is Iowa. It is a replica set of 3 nodes and all the goodness that comes with Atlas. It truly takes a globe. I would like to thank everybody from Google, Exafluence, and MongoDB.